Yes, if I don't hear otherwise, I assume here. And so, okay, great. So today I'm talking about something about quantum gravity, but given that the audience of the conference is supposed to be pretty broad, ranging in a various subfields, and that the talk is the first one in the conference accidentally. So I plan to start from some very elementary review, which many of you probably know very well. But then I present some main claims in a kind of high-level form. And then towards the end of the talk, I started becoming a little bit more technical content and then wrap up. So hopefully this works. Yeah? Okay, as we all know, two pillars of modern physics is quantum mechanics and general relativity, and they are not get along very well. And one problem is at short distances. As is well known, at the length scale or the Planck scale, like LP is a Planck length, the theory loses control. So you need infinite number of free parameters to make theory finite, and then description based on the point particles in continuous spacetime is broken at that scale. And that we believe that basically the main line of addressing this question is like string theory. And even the current formulation, we have perturbative string theory and so on, is on the right track, which we feel from various evidence. But the content of today is some other problem, which can happen even at long distances. Okay? If you have some very strong gravitational force, and you can have a horizon where you cannot causally access certain regions if you stay in certain space-time regions, and then you have some structural problem reconciling quantum mechanics and gravity. And this is broadly known as a black hole information problem, and that's the theme of this talk. So what is a black hole information problem? And that has to do with the third pillar of the modern physics, that's statistical mechanics. Think about the black hole, okay? The black hole doesn't have detailed structure at horizon, as a phrase as a no-hair theorem. And imagine that we just throw some box filled with radiation, namely having some positive entropy, into the black hole. And then black hole will absorb that and then become some new black hole, which is slightly larger, but still black hole. So you may think that entropy is not there because of no hair. And then that means that the entropy went down by throwing radiation into the black hole. Okay, that would be the violation of statistical mechanics, okay, second law. So the major progress happened in the late 20th century is by the proposal of Jacob Bekenstein, and he proposed that black hole in fact has entropy, which is proportional to the area. Okay? So this S black hole is area of the horizon. Okay? So this area is the area of the horizon of the black hole, and in units of Newton constant. That's a Planck length. And Planck length in our universe is a very, very small, short, 10 to the minus 33 centimeter. So this entropy is a huge amount of entropies, because area in unit of the Planck length. And indeed, he could show essentially that if you sum up this entropy of a black hole and that of matter, in this case, it's radiation, and then the sum of these two quantity is monotonically increasing or stays, I mean, it's non-decreasing. Okay? The exact proof had to wait some decades, but essentially that's the message, and he essentially showed that. Okay? But then, does it make sense? Because if the entropy is given in this finite quantity, okay, and if you take a derivative of the entropy with respect to energy, which is just a mass for black hole, and then area is 4 pi g Newton m square, okay, that's the area over 4 g Newton, you must get some finite number. Okay? And entropy, take a derivative with respect to energy, must be inverse temperature. But it's not true that the black hole just absorbed stuff. Then temperature cannot be there. If there is a temperature, then of course black hole must be irradiating. This is a famous, of course, Hawking's discovery. And there are detailed calculation I will just totally omit. But the basic message important for this talk is that if we assume that the horizon is smooth, in the sense that if you're falling in and then you don't notice anything at the horizon, okay? Nothing very special, like not like a surface of the material or stars and so on, you just go through, okay? Because of equivalence principle, because horizon is nothing other than just the boundary of the highest speed thing you can reach to. It's just almost empty space. If that's true, under that assumption, if you view this object, black hole object, from far away, then you must have some radiation with a temperature of this much. That's exactly the number you would get from thermodynamics, ds, dE. So at this point, the black hole the thermal object, that seems to be established. Okay? That's a big deal because entropy especially goes like a horizon. So that means that this horizon seems to have some degrees of freedom, but the horizon is a space-time. It's just locally nothing other than just empty space-time. So the space-time itself has entropy, okay? Or microscopic degrees of freedom as a real physical entity. Okay? That's what this means. But it led to famous problem. And according to Hawking's calculation, and this radiation is the same no matter what initial state is, as long as this macroscopic property is the same. Say same mass, you can just collapse a desk or some chest to form the black hole, the same mass. And then because black hole is the same mass, and then the final radiation is exactly the same. Okay? So that means that the radiation, forget about information of initial state. And you may think, who cares, it's just information is lost. No, this is a big deal because that means that the time evolution is not one-to-one. Okay? From two different initial states, you can go to exactly the same final state. That means, especially if the nature has a time reversal or CPT reversal symmetry, then you can't almost do science. If you reverse it, the statement corresponds to same initial states go to two possibly different states. Okay, you can't do physics in the usual way. Okay, in a technical world, it's not unitary. Okay, so this is the original form of black hole information problem, and that was a big thing. Especially because the calculation Hawking adopted is done in the regime we traditionally believe that both general relativity and quantum mechanics is true. Yeah? So unless something is terribly wrong, it seems to be this conclusion was inevitable, and yet this conclusion seemed to be unacceptable. Yeah? But the physics of the black hole itself provided the answer to this conundrum. So remember that the entropy of the black hole went like surface area of the horizon. This is crazy if you think a bit more carefully, because if the space-time composed like a lattice of the Planck length size, then what's the entropy? You can put or not put a particle at each site. So then the number of possible states is 2 to the volume in unit of Planck length. And if you take a logarithm, that's the entropy, it goes like a volume, okay, in Planck units. Of course, you learn that the entropy is extensive quantity, and this is what you would expect. And this number is much larger than the area, because in Planck unit, this is a square, this is a cube, okay? So this means that the concept that the space-time exists down to Planck length in a usual way is just an illusion, okay? You don't have that much degrees of freedom, okay? So you may think, oh no, why not just to put in the material on all these sites? What's wrong with that? And if you try to do that, way before filling up all these sites, the black hole forms. And if you want to add one more particle, the simply black hole becomes bigger. Okay? So you don't have this kind of classical space-time down to this short length. That's just an illusion. Quantum field theory is terribly overcounting degrees of freedom. Okay? And that suggests that because degrees of freedom goes like area, you may think that the theory of quantum gravity may be formulated in one less dimension. That's called holography, as you all know. And that sounds completely crazy. Yeah? But in 97, Juan Baltacena came up with even an explicit example of these things called holography in ADS-CFT duality. That's applies in limited case that if the space-time is asymptotically ADS space, I think everybody knows ADS space is a space with a negative cosmological constant. If you approach that special space ADS at infinity, and then that physics in the interior is just rewritten, mathematically equivalent form, rewritten in the D-dimensional theory without gravity. Okay? In this case, a very special theory called a conformal field theory, but it's just simply a class of field theory without gravity. Okay? And the funky thing was that this correspondence was that some geometric quantity, like area and so on, and in ADS bulk, was actually related with the quantum information and conformal field theory, as the chair of this session figured out, yeah, with Sensei Lu in his pioneering work. Okay, so according to this, black hole evolution must be unitary. Why? Because no matter what, you just form the black hole and then wait it, and then you just Hawking radiation come out from it. You can just simulate this in conformal field theory. Yeah? You must be able to have some explicit mathematical map to go to conformal field theory and then simulate the same thing. And we know that quantum field theory is unitary, okay? Usual quantum theory, because the theory does not have gravity. Okay? So this is a normal quantum theory we have. So in this picture from the boundary or holography, and essentially what happened is the following. Now it's a quantum level, black hole, think about the black hole in quantum level, you have a Hawking radiation, but because of the gravitational potential, some of the Hawking radiation is trapped near the black hole horizon. This is black hole horizon. And so let's call this is a Hawking say cloud. And you have some region. And the temperature of this Hawking cloud locally is higher and higher and higher near horizon because of just gravitational pull shift. Okay? So at some point it becomes even string scale temperature where the clearly space-time description, the classical entity just breaks down because temperature is already string scale. And if you throw something in, what happens? Then if you throw something in, it slows down because of time delay, yeah? And then it's absorbed into the horizon because everything resolved. It's a super hyper high temperature. And then it absorbed into the surface of the black hole. And then surface state, just remember initial state, and then coming back as a whole. So essentially, the horizon in this picture behave as usual material surface. So clearly no issue with unitarity. Yeah? Of course, with at least no contradiction to assume that every physics is unitary, because you have some surface which behave like material surface. And we are seeing this phenomenon everywhere. Okay? But then the question is, what about the interior? Is it not true that if you're falling into the horizon, then general relativity tells you that you don't feel almost anything except for tiny, tiny tidal force and for large black hole. So what's going on? It's unitary, it's fine, but then are you telling us that the general relativity is just totally wrong? Or if you take a general relativity's prediction super seriously, then if you go through and then nothing you see, and then Hawking's argument applies. Yeah? In that case, it seems like there is information loss, and then unitarity is not true. So what was wrong with Hawking's analysis if that's not the case? So these are the two ways to view this question. So you see that real issue is incompatibility between unitarity of quantum mechanics and equivalency principle of general relativity. Okay, so these are doesn't seem to be compatible. So the main claims today is that the first one is in quantum gravity, a system with a black hole, or more generally with a horizon, accommodates two very different descriptions. Okay? It looks completely different, but the two descriptions are in fact physically equivalent. If you ask any physical questions, you will get the same answer, but sometimes in a very different way, apparently. Okay? The claim two is that in this description, only one of quantum mechanics or unitarity or interior space-time general relativity is manifest. The other one doesn't seem to be there, but if you think about things carefully, the other feature arises as emergent dynamical properties of the system, whichever the one you didn't take, okay, as a manifest. That arises in a non-trivial way. Okay? So those are the things we will see today, building on, of course, a lot of recent works done by many. And then later, I focus on one of these descriptions, which I call a unitary gauge construction in detail, and then go to, because that's what I've been doing. And it's, we see more technical detail about it. Okay. So the talk is based on mainly on these two articles I wrote at the end of the last year, where you can see more complete difference and so on. Okay. All right, so let's look at the first picture, which is done mostly by others. So I'm reviewing maybe quickly because of the time constraint, because some others will certainly talk about it. So that's based on a global spacetime. So this framework starts from the picture suggested by general relativity, namely you have global spacetime. So think about the quantum mechanics. An equal time hypersurface goes through both exterior and interior of the black hole, as suggested by general relativity. General relativity essentially suggests this, sometimes called nice slice, so on. Nothing wrong, because all the curvature, invariant, everything is sub-Planckian. So you can consistently think in the low energy context, this kind of surface. And this is a Penrose diagram. As you know, the light rays travel in 45 degrees. So any material field travel more vertical than 45. So inside this region, anything hit the singularity. So this blue region is inside the black hole. Okay. So this equal time surface goes through both exterior and interior of the black hole. Okay. But now we start learning that this kind of description is highly redundant. One way to view this is that if you think about late time surface, you can take a surface completely consistent with general relativity, that interior volume goes to even infinity. Okay, so very large, keeping area finite. Okay, so this means that the volume is huge. Means that you can have various different excitation in different locations. So you can have a lot of different configurations, which seems to be beyond the Bekenstein-Hawking entropy suggested by area. Okay? So this seems to be a contradiction. But that's not the case. You start learning that in a semi-classical level, there are two states which are orthogonal, completely orthogonal. Like if it's just the particle is excited in different location, a dagger of some x and a dagger of y is completely orthogonal. But these are not actually completely orthogonal in quantum gravity. It has exponentially suppressed, so it's a non-perturbative effect, exponentially suppressed overlap between these states. And if you diagonalize these things, and most of the things are null states because of the huge gauge redundancies of the theory of the gravity, and only EWS independent states remain. Okay? So that way, this description is super redundant, okay? In a sense that you have to divide by gauge theory. And you can see the same thing from the other side. This is one argument. From the other way, let's suppose that the number of independent state is just the e to the s. Yeah? And then you just consider generic superposition. Okay, Ci psi I, so Ci is 1 over square root e to the s. Okay, and you take inner product of these two, so it's becoming like this. Okay, so size of each coefficient is 1 over square root e to the s. So this quantity has absolute value 1 over e to the s. And then you sum up with a random phase. So you have only square root coming from it. So it's exponentially small overlap. Okay, even if these psi 1 and psi 2 are not orthogonal. Okay? To take the generic two states, and then it's almost orthogonal. So that's the way you get a huge amount of apparently orthogonal states, which is literally orthogonal in the limit that you ignore exponentially suppressed correction. Okay? So this is really confusing, and then it's misleading. So let's see how the unitarity, the statement of unitarity corresponds to in this picture. Okay? Existence of interior is obvious because I started from global spacetime, right? Okay? This equal time slice going to interior and exterior. Then the question is unitarity. So what's the unitarity statement corresponds to in this picture? So let's imagine that you have some sub-region R, which is outside the black hole essentially, so radiation region. And then Hawking radiation can be viewed as a pair creating two particles, positive energy, negative energy. Negative energy is fine because of near horizon region, because it's not very flat space. And then those negative things falling into the black hole, yes, keep producing Hawking radiation. Okay? That means that entanglement entropy of the R, that's defined by reduced density matrix on R, rho, and taken trace. Yeah, that's the definition. And rho is just integrating or tracing out the R bar in the global state side. Okay? And that's essentially the number of EPR pairs R has. Okay? But but EPR particle R has, but its pairs are in R bar, okay, complement. So that number of those kind of EPR pairs is essentially captured by this, and that's keep increasing, yeah, because it's a pair producing, pair producing, pair producing. So as the time goes on, this SR, entanglement entropy of the R, should keep going up. But if unitarity is correct, then final state, let's assume that initial state was a pure state of just some collapsing material and formed a black hole and then completely evaporates. After evaporation, you don't have a black hole. Okay? So this R outside region or full region must be, any particle must be entangled with the pair inside R. There's nothing called R bar. So the entanglement entropy of R, maybe the number of EPR particle whose pair is R bar, is 0 because you don't have even R bar. So you should go back. Yeah. So that's what Don Page predicted. It's called Page curve. So the question boils down to the statement how to get this Page curve, okay, in this global picture to see how unitarity is recovered. And that's recently done by these authors, including it's all young stars. And so here's the way they got this thing. Let's imagine this state on R, reduced density matrix R, that can be obtained in the path integral, in Euclidean space. If you do Euclidean path integral, you can prepare the states on this subregion R as a function of the field on this upper edge, upper of this line on the lower, approaches from lower, and then you have F, and that will give a functional of the G and F. I is just species index. Yeah. So that's essentially density matrix states. This corresponds, of course, Brand get is F and G because field configuration specifies states. Yeah. So then given that, and you can compute SR through formula, trace, log, 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 but you can equally get the same thing in this expression. You take the nth power and then take a trace and log, and you can easily check and this reproduce to this in a limit of n equals 0. And that's useful because you have to take log of the trace, which is number. Yeah? Certainly much easier than a log of the matrix, which is a reduced density matrix. Yeah? So let's compute the first log to the n and then take a limit. So let's consider n equal 2 case and how to do it. And suppose you just make eigenstates Fi of the Euclidean time evolution. Yeah? So then rho square means that if you go to the column of the first matrix and go to rho, and then rho goes to column, and the column goes back to rho, and it's grew into the column, right, to take a trace. Yeah? So this is a diagram. And if you compute this for rho square and rho cube, similarly, like 3 sheets, and if you analytically continue and go to n equal 1, you exactly reproduce Hawking's result, as you may expect. But these guys did was that no, because theory of gravity, you have to add up all these configuration, which is topologically even different from this. So for example, you can have some wormhole between these two seats. And then because this is topologically higher order, it's exponentially suppressed. Compared with this, it's e to the minus s black hole. But now you can see that you can have 2 cycles. Okay? This cycle and that cycle, if you a little bit think about it, and then these things. Separately, you can have cycle, and then on this R, you can have F and G, and you can have a lot of different configuration F and G, and you can do it for 2 of them, so it's equal to 2R, okay? And then entropy of radiation. So at the late time, precisely at late time, where the radiation entropy becomes bigger than black hole entropy, dominance changes. And this replica wormhole, something called replica wormhole, dominates, despite the fact it's naively non-perturbatively small compared with the reading effect. So the Hawking's quote-unquote mistake was he ignored this topologically non-trivial correction. So that's the way to see unitarity in this framework. Okay, so from physical point of view, what this is really doing? What this is really doing is that, okay, Hawking radiation coming out and a particle keep being added in R, and then later Hawking radiation, pair production, okay, it's a pair and it's added. But in order for entanglement to come back, because at the end, everything must be purified by its pair inside R, means that this thing has some pair inside R at the late. So that means that this guy is entangled with the both, which is not possible from monogamy. Okay? So that means that these two things, apparently naively independent thing, is outside and inside of the black hole. These degrees of freedoms are not independent. So that's the consequence of this. Okay? As was noticed by many, and especially emphasized by Matsushima and Susskind, this means that the Hawking radiation emitted is actually not completely independent with what you think is interior degrees of freedom of the horizon. Okay? And in hindsight, of course, that's what you need, because if information were preserved, and we are taking this global slice, global space-time slice, and then Hawking radiation must contain information if information is not lost as viewed from exterior. So if you have a falling object and then a complete information object is here, and object itself goes through, so on this surface, information is copied, that is not allowed by the cloning theorem of quantum mechanics. And this is consistent because with the observation, because no one can see the both at the same time, because of the causal structure of the space-time. Okay? So the summarizing, in this picture, starting from global space-time, namely general relativistic picture, and embracing interior is there, but then unitarity is not obvious, as Hawking's kind of thought, but because of this replica wormhole, not but at the effect of gravity, then in fact the theory preserved unitarity. And so that's the way you view the things in this picture. Okay. Now, in fact, you can start from the other way. That's what I call Unitarian reconstruction. Let's consider you see the black hole from exterior. That more or less corresponds to holographic view from boundary, from far away, you see it. And as I argued, as we see, if you just throw in an object, it throws down, and throws down. And at the classical level, it can even never reach the horizon because of infinite time delay. But in the quantum level, that's not the case because you have a Hawking radiation and hence Hawking cloud. The temperature of these things approaching the string scale near the horizon. So it will be absorbed into this, which is called stretched horizon. Okay. So this object is Planck distance away from really mathematical horizon 2m Planck square in Schwarzschild black hole. And then it's absorbed this and then emitted, and then bounce back, and then becoming Hawking radiation at late time. Okay. And this Hawking cloud, the region where Hawking cloud is there is sometimes called zone. So let's just remember this word, it's zone and stretched horizon. Yeah. But the point is that the degrees of freedom outside the horizon is the entire thing, because classically you cannot even go to the interior. Interior doesn't exist. It takes infinite time yet classically. Even quantum mechanically, it's just absorbed into these degrees of freedom and come back. Okay? So the time evolution of these degrees of freedom is completely unitary. Okay? No complication of interior or anything like that. But of course, then the question is how the interior picture emerges in this way. Yeah? So the problem is the other way around from the picture based on replica wormhole and stuff. Okay? And that's what I've been doing with other researchers as well. Okay. So there are a couple of key features to realize this emergence of interior. It's very important. Okay? In fact, those features are defining characteristic of black hole because interior spacetime doesn't exist. So what's the black hole? You cannot answer that there's a spacetime region in which nothing can come out. That kind of spacetime region doesn't exist in this way. So what's the black hole is the emergence of the following properties. The first, because of the huge redshift, okay, as viewed from exterior, then it's a redshift. So all these different states is becoming dense and dense, and exponentially many density of states okay, as viewed from exterior. And that's nothing other than certainly the Bekenstein-Hawking entropy. So you have E to the S Bekenstein-Hawking match of the states in some very small energy window. That means that energy difference of next level is exponentially small. And you need exponentially long time to discriminate these things. Certainly just the uncertainty principle, delta E, delta T equal H bar. So you need exponentially long time, but if you spend exponentially long time, by then the black hole is totally evaporated. Okay? So to keep the description that the black hole is there, that kind of description necessarily kind of coarse graining all these exponentially small the states. Okay? And you're just only focusing on some big jump excitations. Okay? So let's divide some excitation in a zone where this black hole Hawking physics is relevant. And here, most of the mode is soft. Okay? It's smaller than Hawking temperature as viewed from exterior. Let's call soft mode. And then hard mode is a mode, excitation whose jump is bigger than, sufficiently bigger than Hawking temperature. So then you can, of course, discriminate this in a relevant time scale 1 over Hawking temperature. So those we call hard mode. So roughly, this hard mode is just an object, okay, in this zone region. And soft mode is something you cannot discriminate. Okay? So clouds. So it's like a micro state of the black hole. Yeah? So the semi-classical theory describes this hard mode physics. And the far region is, okay, it's just far away. So this far mode is still there. Of course, some excitation far away from black hole, which is usual mode. So you have this structure, okay? And you can effectively describe only hard mode, almost necessarily because of this phenomenon, okay, of exponentially dense states. The second feature is that because the temperature, local temperature, now not as viewed from exterior, local temperature near here is a string scale. So dynamics is string game. You don't know the detail what's happening. But we already know, because of these people, that this has some characteristic features. This dynamics at the stretch horizon or string scale dynamics has very characteristic properties. It's very chaotic, quantum chaotic, and in fact argued to be maximally quantum chaotic, saturating bound. And it's fast scrambling, namely that chaos is reached very fast. It just immediately becomes this chaos state, and universal. Namely, this doesn't discriminate some low energy species. Okay? It's not like photon or neutrino. It's the same for the string point of view because it's just all low energy excitation string. Okay? So it's acting the same way. Other than gauge symmetry and space-time quantum numbers, it doesn't discriminate any low energy species. Okay? A particular example is that there's no global symmetry. That's important, crucial. Okay? And because of this, and what happens to these modes, soft mode, hard modes, is that these are becoming generically entangled states. Okay? Suppose your hard mode states, okay, is slightly higher states, you can compensate by soft mode states being correspondingly lower states, keeping the energy of the full state in the same energy, near energy bound of the microcanonical ensemble. Okay? And given this, if you just focus on hard mode, you see that it's exactly reproduced thermal physics. Okay? In fact, this is a mechanism. Hard and soft mode is totally generically mixed and entangled. So even though the full state may be pure, if you focus on hard mode, which semi-classical theory describes, and it looks like just a totally thermal. That's why semi-classical theory view black hole as a thermal state. Okay? And again, the important point is that that happens to all the species. It's not like a photon is thermalized, but neutrinos are not. Okay? The sun's surface is probably like that. Okay? So this is much stronger concept of thermalization than what we usually use in condensed matter theory or something. Okay, thermalized, but neutrino may be just going through. It's not. All the species universally becoming this kind of state. That's why it can be reinterpreted as into space-time layer. Okay? It's quite universal. So the high-level argument, like when how the things works, is the following. It's well known that in the Minkowski vacuum, namely there is no high energy excitation and so on, can be rewritten in terms of the accelerating observer on the right. So accelerating like this, so this observer never see anything outside this horizon because these guys, outside guys go like passing through. Because this guy never see that. And in this picture of the left observer and right observer, that looks like a thermal state, thermally mixed, thermally entangled states called thermophile double states. Okay? So that's why this guy feel the radiation. It's called Unruh radiation. You must know it, and thermal states. So essentially, what's happening in black hole in this picture is the other way around. So you have hard mode and soft modes universally entangled in a way that it looks thermal. Okay? Therefore, if you change a frame, it must look like a vacuum. Okay? So you can just falling through the horizon, nothing is there, it just goes through. Okay? And that happens to universally for all low energy species. Okay? That's how the near empty space-time shows up. More precisely, at later times, the black hole, the soft modes, also entangled with early radiation, okay? Because emitting Hawking radiation emitted, say, from here. I mean Hawking radiation emitted here and becoming free particle, okay? Not Hawking cloud. Hawking radiation is keeping being emitted, and then those things are also entangled with this, and then the soft plus radiation is viewed as kind of whichever left. Corresponding to a hard mode, because hard mode is the only object which you just see in a semi-classical theory, and that has a pair. So it involves early radiation, as we saw in the other description. This Saskin, EPR type thing, early radiation is involved in this. So you get the same thing in this.
Nomura-san, can I ask a question?
Oh.
So if we think this separation of hard mode and soft mode from CFT viewpoint, how can we distinguish these two degree of freedom?
Oh, you have to really do really like experimental thing is ultimately, it's not practically. If you see some probe going on, something you can discriminate as an excitation and the time scale that the black hole is still there, in that kind of mode, you just have to separate out. And everything else is a soft mode. So I don't know what's the best way to do.
Yeah, I just wondered, are there any some kind of known example where this soft mode and hard mode are entangled, like the way you explain some example which we know?
Chaos.
Chaos.
Yeah. Oh, you see it. Maybe next slide.
Okay. Yeah.
So more details. This seems to be a kind of force, but more mathematically or with equations, let's consider some black hole vacuum states. Namely, this is a state viewed as a black hole without an object at the semi-classical level, whatever that means. Okay, let's consider black hole vacuum states, and which has a lot of black hole vacuum states, and which is just, let's consider soft mode and hard mode. It can be viewed as a different mode. So you can consider creation annihilation operator for different modes independently. So hard mode state is specified by occupation number n of the hard mode, and soft mode, okay? The states are labeled by I for each configuration and alpha of the hard mode and radiation, and it's entangled generic way. Okay? C, coefficient C, which generically entangles soft mode and hard mode. If it's a chaos and around the stretched horizon, this structure is already, if you don't have any specific structure, this is what you expect. Okay? You just write down the most generic states with the same size of the coefficient for each time, every time with a random phase. Okay? That's all I assume. Okay? That's the assumption motivated by this quantum chaos and fast scramble and so on. Okay? And then with this, because of course hard mode state has higher energies, soft mode state must have lower energies. Okay? Lower energies means, of course, S. Bekenstein-Hawking at the n minus E of the hard mode to compensate the fact that the black hole has energy constraint, the fact that the total state has an energy constraint M, yeah? Because we're talking about black hole of M. And then, so for hard mode, higher hard mode states have a smaller number of soft mode states entangled. Okay? And therefore, if you just canonically normalize these fields, you just get really or you're just integrating, tracing out these states, and then you just get the thermal states with the correct Boltzmann factor. This is nothing other than just usual statistical mechanics. And then if you see some small system with the generic states, then of course you see the thermal states, nothing other than that. And hard mode is a small system because they have a big gap. That's not like exponentially dense gap. That's the most of the black hole states. Okay. Okay. So this is a state I was thinking about. So the black hole microstate is nothing other than the microscopic way for these hard and soft modes are entangled. Okay? Still keeping generic way, you can have a lot of different ways to entangle at the microscopic level. The number of the states e to the S total, that's like soft mode coarse-grained entropy times radiation, early radiation coarse-grained entropy. That's the mostly the coarse-grained entanglement, coarse-grained entropy of this black hole microstates. Okay? Now, this is a vacuum state. Remember that we're talking about vacuum state. The black hole has mass m, but there's no object in the sense of semi-classical theory. Okay? Let's just think about some generic state only under the energy constraint of the full state being m, of energy m, ADM mass m. Yeah? Then this is a generic state. And that's the state, because it's so generic, we think that there's no excitation. So generically like this. And then yet, if you focus only on hard mode, it's a thermal state. You can have, of course, higher excitation, but still vacuum. And now how to describe excitation on top of it. For the hard mode, namely the object in the zone, it's obvious. Usual creation annihilation operator for this. Okay? So occupation number n become one smaller if you act B for particular mode gamma, and then B dagger, it will increase one, okay, for any particular gamma. Yeah. All right, and then far mode is even more obvious. That's just far from it. It's just the A and the usual thing. But what about the interior? Interior, now it's focused on this piece. Okay? This piece is entangled with hard mode states n. N is again a collection of occupation numbers for all possible hard mode alpha. Okay? So that's entangled with this combination. And this combination, let's call this is mirror microstate. It depends on microstate A, but each microstate, vacuum microstate A, you can always define this guy, which is entangled with the configuration N. So let's call it N, say mirror, but it depends on A. And if you canonically normalize this guy, and then plug this back into this blue box, and then this canonical normalization factor will produce exactly the factor which you need for thermophile double states. So then, okay, let's move this up. Okay, so then for these guys, you can just define this operator of creation annihilation of the mirror state for mirror mode for each microstate A. Okay, so that's the okay? So each microstate A. Okay? And then you can compute and then check that using the original definition of this, and this mirror mode obeys canonical computation creation annihilation operator up to exponentially small error. Okay? So remember that this thing is the excitation or the excitation of a collecting mode of soft modes and radiation. So black hole interior emerges as a collective excitation, quasi-particle of the soft mode and radiation in this picture. Okay. Once you get this operator, then it's easy to change the frame. That's the usual Bokoliubov transformation from left-right picture to interior picture by usual Bokoliubov transformation. You can form interior infolding mode operator for each microstate A and A dagger. Okay. So at this point, you have some operators for each microstate, any microstate A, which makes the state looks like exactly thermophile double states. Okay? This is a hard mode in the zone, and that's pair or mirror, and then you can just write down the interior operator. Is that sufficient? Actually, no. For example, your excitation might be entangled with this vacuum mode A. So then the mode operator we just found was for each A. But what kind of microscope operator you have to use? Is it A1 or A2 or A3? Okay? Or in fact, this is a basis dependent statement. If you just write down this in the different bases, and then you have to use the different bases, and you don't have only one microstate. If your falling in object is entangled with the vacuum degrees of freedom, that can happen if this object interact with the early Hawking radiation before jumping in. So clearly it's entangled with the soft modes or some microscopic degrees of freedom. And then you need to be able to find an operator which is described for all these microstates, which is entangled with this evolving object. So let's consider some promoting this operator, which we found for each microstate A, to apply to some class of A's. So first, let's imagine that you have a space of vacuum microstates, which runs by just this psi A. A is again the microscopic index, okay? And the 0 is a vacuum. So you can have a space spanned by all these black hole microstates, or you can consider subsets of this. Okay? So not really like a spanning E to the S total, but it's only E to the S effective. Okay? And I take this effective to be smaller than, strictly smaller than the total black hole microstate number. Okay? And then you can show that you can just define globally promoted operator for each microstate, you have a bit tilde and a bit tilde dagger, and you can just have a direct sum of these things, okay, in this space. And then this operator and corresponding informing operator acts correctly in any states in this empty space. Okay? Not just the basis states, any state, any generic state in this basis states, you can use this operator. And now the point is that for any folding object, which is entangled with microstates, the object has an entropy which is much smaller than black hole entropy. Okay, object entropy is like tiny compared with the black hole's exponential into the area of entropy. So relevant microstates needed for this guy, okay, for this folding object, as you can see from Schmidt decomposition, is much smaller than black hole microstates. You can always take this operator to cover the entire microstates relevant for this folding object. Okay? So with this, you can build the effective theory of the interior. An important thing is that this state, let's say the state, your black hole vacuum microstates take this form at some time t. Okay? And at that time t, you have hard mode, that's the mode on the zone, and this is the salt modes and radiation. So at that time, you just identify these mirror states and operators and so on. So you can elect effective theory at each time t. But that effective theory describes clearly only zone because it contains hard mode in the zone and then its mirror states. That's it. So it describes only causal development of this. Okay. So of course, no cloning problem. You don't have anything. It's effective theory. You already coarse-grained soft modes, yeah? Because it's emergent collective phenomenon. So vacuum looks like unique. Despite the fact you originally had exponentially many microstates, all these effective theory looks like just a unique state. Yeah? So that's apparent contradiction of unique vacuums, informing vacuum states and microstate is just coarse-graining. And this is intrinsically semi-classical, yeah? Because you're describing only hard mode. And it's even not unitary because you already coarse-grained soft mode and so on. You cannot use this theory to describe the theory's infinitely long time. You certainly see even singularity. Okay? So the theory just breaks down because this is not microscopic theory, it's just effective theory. Okay? And in fact, even folding object can go outside this. Okay? If you want to describe these guys, which is not totally contained in this, and you have to elect effective theory in different time, using different soft modes and different hard mode at that time, and you can elect it and you can describe. Okay? So this is a version of complementarity. So a couple of comments about this. So this procedure of electing effective theory, in fact, has some ambiguity, coming from the fact that this bit tilde and operator, mirror operators, is not completely orthogonal to the vacuum microstate in this empty. So you can have some mixture, and that gives you intrinsic ambiguity of electing this framework or this effective theory. That's about the exponential e to the minus s. Okay, e to the minus actually s over 2. And that's the intrinsic limitation of this semi-classical theory. And it makes sense because a black hole is a finite system. Okay, the number of degrees of freedom is finite. So therefore, you cannot have a theory which has an infinite precision. Okay, in fact, even the theory is not defined at this level of exponentially suppressed match. Okay, and the second comment is that okay, we just made a global promotion. So the operator, you can come up with the operator which acts not just specific microstate A, but it's a class of microstate, which is in fact, it's some constant, any constant times black hole plus radiation coarse-grained entropy. So it's almost all the states in this way, unless C is exponentially close to 1. Okay? But this is enough to say that, in fact, because number of state is e to the s, not s. So this means that you cannot cover most of the states in vacuum microstates. Even if you take C to be 0.999999, e to the 0.999999 something is very small compared with e to the s. Yeah? Therefore, you need a lot of these touch cover. It's analog of a cold subspace. Okay? But you can take arbitrary cold subspace in this vacuum microstate because you don't have natural way because it looks all the same semi-classical geometry. Yeah? It's all same black hole. So you can take anything. You don't have natural cold subspace associated with geometry. Yeah? But you need multiple. Yeah? So that's the statement of state dependency emphasized by Pictolimus and Raju. And the final comment is that for a young black hole, which is before the page time, the time which this, okay, the change of the entropy happens, namely where the black hole coarse-grained entropy is still bigger than radiation coarse-grained entropy, you can write down the microscopic operator acting only on the soft mode. In fact, you don't need the early radiation. You can reduce to those modes using something called PET map, but you don't need early radiation. But this option is available only for young black hole. For old black hole, you have to involve early radiation in this effective interior operator. Okay? In addition to soft mode. By the way, soft mode must always be involved. Yeah? So for old black hole, you can use the combined system of soft mode and radiation as a mirror system. For early black hole or young black hole, you can use just the soft mode to mimic the same phenomenon without involving early radiation. Okay? So summarizing this way of viewing, which I call unitary gauge construction, the unitarity is by construction. Okay? So it's like almost holography motivated. You see from outside degrees of freedom is everything. Okay? So therefore, from this perspective, just the black hole horizon behave like material surface. So unitarity is obvious. But why then interior? Because of this property of exponentially dense states with the chaotic properties, generically you have a thermophile double state. Okay? Therefore, you can change the basis to go to the description that interiors show up. Okay? And remember again, for that, its summarization needs to be completely universal. Okay? If there are, say, global symmetries or something, some of the thing may be generated, become chaotic, but some of the thing may not because prohibited by global symmetry. Then this space-time construction doesn't work because for those prohibited particle transformation, the same transformation does not look like an interior space-time at all. Okay? So therefore, because of this, this surface of the stretched horizon is very, very, very different from material surface of the sun or something. Only if with the gravitational collapse, this material surface recede enough that this complete chaotic stringy temperature surface appears. Only in that case, you can just go through and go in without hitting any materials. Okay? And again, the point is that the only thing I assume is this complete chaos. And that's reached in a scrambling time, m log m for standard short field, and no detail, nothing. Okay? No details of UV physics. Of course, I use the assumption that it's chaotic and so on. No global symmetry, universal. That's it. That's enough to reproduce this interior picture. So that's very similar to replica wormhole case that was shocking that we didn't need any detail of the microscopic physics to understand unitarity in the formalism of global space. And here it's similar. Yeah? In the formalism of manifest unitary thing, you don't need the details to get the interior picture. Okay, so now a couple of slides. So structure of the quantum gravity. So now we're learning that you have very different description in existence of horizon or black hole. So global, based on global space-time, which is almost general relativistic picture, and then interior is evident because I started from global space-time. But unitarity is recovered because of non-perturbative effect of gravity. But on the other hand, if you start from manifestly unitary, like holographic picture, then unitarity is, of course, almost by construction, but interior have to be emergent as a collective phenomenon of these clouds, and then sometimes early radiation as well. And in fact, for example, this apparent violation of black hole entropy, like the interior volume is huge. In this case, yes, you have huge interior, but the inner product has a very small ETS, and after diagonalization, most of them are null. That's how this is viewed. Starting from exterior, you have only ETS state from the beginning. So then what's this apparent big volume inside the black hole? That's because most of the state is almost orthogonal. So you see the other way, okay? The same phenomenon. And you can also see this some ensemble nature. This is something I didn't have time to discuss. If you include this wormhole and then you compute some physical quantity, you get the result, which seems to be understood only as something computing the quantity associated with the ensemble. Yeah? Something is 0, but square of 0 is not. Yeah? So that's possible if you only think that this is kind of average properties. In this picture, that's easier to see because of a soft mode. Okay? Soft mode, you cannot discriminate in principle, keeping the picture of the black hole. Okay? If you wait exponentially long time and the black hole evaporates in a Hawking radiation, in that sense, yes, you can discriminate and complete unitary, but keeping the black hole picture, you cannot. So if you take average of the soft mode, you get exactly the same result with the path integral. Yeah? So that's the way you see like statistics of soft mode states, okay, in a single unitary theory, okay? At least in higher dimension. Okay, so why this is the thing? It's so totally different to description in quantum gravity. Ultimately, that's because of gauge invariance of quantum gravity. Of course, in gravity, we already know that we have gauge invariance, huge redundancy called general covariance. You can describe this point as a 1-1 in a Cartesian coordinate, or this R theta. Okay, it looks like a very different 1-1 and square root 2 and pi over 4. Of course, it's the same thing. Sorry, I took this from colloquium, so it's a little bit too elementary. But now, at the non-perturbative level, you can even see that's a different topology because you have a topology changing process. Even different topology is actually talking about the same state, okay? In, say, Heisenberg picture. So this huge redundancy is the reason why these two pictures are so different in the existence of horizon. Without horizon, these two are different, but it's a very minor difference, okay? And it makes only one of the quantum mechanics and general relativity manifest. Okay. So summarizing, what we discussed today is that if you just look at this black hole conundrum carefully, you learn the structure of quantum gravity, namely that's still consistent with both quantum mechanics and general relativity in the regime that's applicable, but in a very subtle manner. Okay? So only one of them is manifest. One is like an interior manifest if you take starting from a general relativistic friendly picture of global spacetime, but then understanding unitarity requires this non-perturbative gravity, especially replica wormhole, which is demonstrated in lower dimensional case only so far, but something similar we expect to happen in higher dimension as well. And it goes well with the path integral formalism. Okay? Because true, path integral is everything's classical. Being everything's classical, you can just start from just a nice slice and then think about and understand the quantum mechanics starting from that. The other is a holographic. That's like unitary, so like all fixing this huge redundancy, fix it. So you start from there. It's like a unitary description of the gauge theory. And this is something like Lorentz gauge description of the gauge theory. And from this case, interior must be understood. And that arises as a corrective phenomenon. And let's go well with the operator formulation of quantum mechanics. So this duality is essentially Legendre duality. Okay? So it's Lagrangian type description or Hamiltonian type description. And in both cases, you don't need low energy details of quantum gravitational microscopic physics to understand low energy physics, namely the existence of the interior and unitarity of the scattering process. Okay? And yet, of course, we want to understand this microscopic theory of quantum gravity as well. And for that, we probably need string theory or quantum information science. We'll be discussing this throughout this conference, which I very much look forward. Thank you.
Thank you very much for your interesting talk and with a very beautiful review part also, very kindly. So let us send, so let us thank the speaker. So I'm muting. Thank you very much for Nomura-san. And it's time for questions. Please ask questions. I saw the question by Shinji. Please start.
Oh, can I ask a question?
Sorry, first, yeah, could you, Nokoyama-san, could you ask a question?
Oh.
I saw this.
Yes, okay.
Yeah. So please raise your hand when you have a question.
Okay.
So I have a stupid question. So you consider soft mode and hard mode, and so the energy scale of the soft mode is related to somehow page time because you want to discriminate in page time.
Hawking temperature.
Okay.
Hawking temperature as viewed from X.
Hawking temperature. Okay.
Of course, it's locally Hawking temperature blue shift. So these soft modes are below. So all these soft modes are mostly localized at the stretch horizon. So you could say it's just stretch horizon mode. because a blue shifted temperature becomes higher and higher and higher and higher and higher near the horizon. And if you integrate out the coarse-grained, even coarse-grained thermal entropy down to stretch the horizon, you precisely get the area over Planck square.
I see.
Without coefficient, you cannot.
Yeah, can you discriminate in space-time, just in space-time, or?
So here, like 1 over Hawking temperature is a time scale for emitting single photon. And after single photon, of course, black hole state is even different. So if you want to talk about the black hole states or something, and then it changes with this time scale. So it's a natural time scale. It's something, anything can happen in a time scale 1 Hawking photon emission, which is huge in usual microscopic physics. And then you can elect effective field theory, and then you can discuss everything within that effective theory framework.
I see. And also the spectrum of the soft mode, detailed spectrum plays any roles, or it doesn't matter?
No, because almost soft mode is near here. So gray body or something is really like almost negligible. So it's really like a thermal, and then it's most of the things coming from space horizon. Because
I mean for the recovery of information.
Oh, recovery of information is something soft mode must be becoming far mode here, and that like how it's literally going on. You can view this, say like a qubit model. Like if you emit the Hawking radiation, which has a positive energy, so you can have a negative energy, and you can define what the negative entropy is, and you can write down all these things. But the microscopic dynamics clearly is not, cannot be described in this.
Thank you. Thank you for the nice talk.
Thanks.
So Izuka-san, could you ask a question?
Hey, can I ask a question?
Sure.
So I have 2 questions. So one is simple. So can you just tell me what is precisely your definition of the zone? That's the first question. And the second question is that, so I think I roughly understand what you say about the entanglement structure between soft mode and hard mode, and well, precisely hard mode and soft mode and radiation entanglement structure. And by using that, you create the interior mode. But I'm also wondering what you say sounds very much similar to what Papadodimas and Raju is.
Yeah, exactly. Yeah, I'm recording this.
Right. But, yeah. So could you also comment on what is the difference of your proposal?
Yeah.
And also
identification is. I mean, in the paper you see. I mean, all these discussed. I mean, what's the difference? For example, identification is different. Okay. So identification mode of exterior, first exterior, and second exterior of the effective two-sided description is different from pairs, and that's crucial. In fact, you don't get the same phenomenon. But you know, they did a lot. I don't want to you know, kind of minimize a thing, and it's a very beautiful paper, but its identification is different, for example, and variance as well. And
so identification of what is different?
For example, what's the mode corresponding to first exterior, and what's the second exterior of the effective two-sided picture?
What is the first?
The only hard mode is a first exterior, and second exterior, it's soft mode and radiation. Okay. They're using radiation as a first exterior because it commutes with, but I don't want to minimize it, but it's different.
Okay, so your pickup choice is whether energy is bigger than the Hawking temperature. No, that gives the difference between hard.
No, even whether first exterior or second exterior, which one to associate radiation is different. So their thing is actually, if you read carefully, it's not ER-EPR. Okay. And also different from ER-EPR is that like pair is purely radiation. That's Madasena-Sasaki can imagine, but it has to involve the soft modes.
So can we say that the difference is the choice of the basis is different? Can you say that? Choice
no, basis is random. Basis is random. Because you don't know the basis of soft mode. It's just a generic, any basis.
No, your choice of the reference for the hard mode, which is entangled with, say, your soft mode and radiation. That gives a difference. That's what you're saying, right?
Yeah, that's the biggest difference.
Okay. Yeah. And what is the precise definition of the zone?
There are others, but
yeah, what is the precise definition of the zone?
Oh, zone is like if you write down, for example, in Schwarzschild black hole. That's also discussed in appendix of one of my papers. Let's look at, for example, the Schwarzschild black hole. You can write down that in the effective potential, gravitational potential, and then you have a peak. That's about 3m. The horizon to be 2m in Planck units, and then 3m is the location of the peak. Okay, and there you can have some thermalization and then leakage as a Hawking radiation at 3m. So in the black hole, in 4-dimensional Schwarzschild black hole, this is 2m and this is 3m.
And you're saying that in the zone there's the information of the microstate?
Oh yeah, this is by the way, this microstate is sorry, soft modes are microstate.
A soft mode is there in the zone.
Yeah, more precisely the way that these hard and soft, because for each hard, you have a lot of exponentially many soft modes, right? Because it's just exponentially dense. Okay? The way these two are precisely entangled is this index, that's the black hole.
Okay. So you are saying that even just outside of the horizon, up to the zone region, there is a microstructure difference for the black hole. That's what they're creating. Is that correct?
Yes, but most of the difference is at the stretch horizon, as I said, because soft mode distribution is the T cube, right? So entropy equals to T cube, and T blue shift like crazy. So most of the thing is here.
Okay.
So zeroth order viewpoint is that microstate is at the horizon. That's fine. But it's important that order one thing is going to here because Hawking radiation coming from here. Therefore, like Amp's argument that something is a semi-classically propagating here or something is wrong view.
Okay. Okay.
For some purpose, it's important. Those are also different from the previous works. And so, one example.
Okay. Okay. Thanks.
Okay, so then, Tomonori, could you ask a question?
But Hoto-san had the question in advance.
Hoto-san.
Hi.
Please.
Hi. So I have a question about a replica wormhole solution. So you just consider the GR or Einstein gravity theory? Then I'm wondering, do you have such an Einstein replica wormhole solution? So I know you have such a wormhole solution in a JT gravity or 1+1 dimensional gravity theory, but do you have such a realistic solution?
Okay. This is, but first of all, this is not my work. I just
okay.
But this is like after like doubling this space-time because we want to compute the rho square, and you can find a solution. This is a space-time wormhole. Okay, it's not like Einstein-Rosen bridge, which is a spatial wormhole.
Okay.
This is a space-time, okay? and you can have such a solution.
And then you have such a solution. So you have an express solution for replica wormhole in Einstein gravity theory, right? So you get such a saddle point solution in Einstein equation.
In a higher dimension, I don't think.
Oh, higher mean, you mean 1+3 dimensional case is a higher mean? So
no, well, it's, what they have done is a 1+1.
Okay, I see.
And so guess is that this will, but this kind of replica wormhole can prove some quantum version of some Takayanagi stuff. I mean, it's the chair thing. And then that argument of this quantum extreme surface you'll probably hear later would work higher dimension as well. But you don't have like this kind of microscopic wormhole in higher dimension, although people are arguing that something like this is happening in higher dimension, say Tom Hartman and so on, and which I'm very sympathetic, but it's not kind of shown.
Okay, thank you.
And this wormhole is, by the way, anyways, the way to kind of get to capture averaging properties of these. This is a way to capture. If you want to do the microscopic physics, this wormhole would not be enough. This is already averaging.
Also, Shigemori-san, do you have a question?
Yes.
Please.
Hi. Hi. Thanks for the talk. So, how much of what you say apply for extremal black holes?
Interesting and good question. And then I have some tentative answer. So, at the risk of saying something in the end not completely correct, let me just answer. So, but many of those things are just, just applies because it's just simply. But like this piece, for example, like soft mode is the origin. Soft mode, a different configuration of soft mode being complete origin of the Bekenstein-Hawking entropy. That's most likely not true. Okay? And a super hyper near extreme black hole is just a quantizing area. This is a work by Gustavo Triaci and the company. Just the area piece is like soft mode is a temperature above it, but it's a zero temperature limit or very close to temperature. And then area, quantized area is really like saturating most of the Bekenstein-Hawking entropy in that case. So if you just dimensionally reduce those things, then it looks like not the statics of the soft modes, but the statics of the theories. It must look like that, as in JT.
Statistics of the theories.
Yeah, probably in lower dimensional, after dimensional reduction. That's my guess.
What does that mean? So you have to consider different. You have to consider ensemble of
theories. Yeah, unitary theories. Yeah, that was known. That was like Stanford, and that was what you found in JT gravity. That's because that's contained by extremum black hole. Okay? So this is a non-extremum. The black hole is just the statics of states.
Okay, in the case of the non-extremal black hole, you have this temperature scale, and you can. So what sets the scale? So you don't seem to have a
Hawking temperature.
No. Not in the extremal case.
Oh, extremal case, yeah. So that's also the things that doesn't apply. So therefore, it's not soft mode which carries the dominant Bekenstein-Hawking entropy. No.
So you cannot
way to.
So there is no clear distinction between soft and hard modes in this extremal.
No. You have even more degrees of freedom. That's just the area. Area is a continuous number. Okay.
Sure.
And that you quantize it, you have a discrete, and then you take a logarithm. That's the entropy. That's the dominant one. In that case, even zero temperature, you have exponential degeneracy.
So you still have soft modes.
Yeah, you could say it's a soft mode, but it's not like you can view this as like very soft particles of the.
Sure. Oh, yeah. Just like
so. In certain sense, it's just a price, but certain sense, it's different. My guess is that it's not exactly the same. Okay. But the qualification is that I don't really know.
Okay.
Yeah, this is a good thing about conference. So I'm just saying something not on set. But, yeah, that's my feeling right now.
Okay, thank you.
Okay. Tomonori, do you want to ask a question? But after that, it's good time. So please start your also talk.
Oh, I see.
Yeah.
Oh, thanks for the nice talk. I mean, you haven't talked about what I wanted to talk in the next time in my talk. Anyway, okay, I just wanted to ask, what is the boundary condition for these soft modes? I mean, in order for this dictionary between these two gauges to work, do you impose some ingoing boundary condition for the soft mode, or?
Oh, it's just like a stretch horizon is almost in some sense reflective, right? Because there is nothing beyond that. And then the other is a gravitational thing you have. So it's kind of trapped mode. And of course, how it's is a physics. You don't really know.
I mean, okay, I'm wondering whether or not that we can impose such a boundary condition within the framework of effective field theory, because near the stretched horizon, then there are these stringy dynamics going on, and
yeah, so we don't really know, but it's a brick wall. It's called brick wall model. We just simply have some this is the end of the space time. There is no degrees of freedom.
Okay.
So like reflective boundary condition and so on. Of course, you're looking microscopic information. It's just.
I see.
But you can't describe that anyway.
All right.
So the old microscopic information is beyond that.
Thank you.
By the way, Nomura, can I think your soft mode as a kind of edge mode of gravity?
That's interesting. Yeah, I think that's one of your work, and always my thinking is always in a form. If you see things from distant, in fact, the same for those in a static patch, then you have just a microstates, a lot of microstates, okay? And then for any of these microstates, you can go to the like maximal extension, okay? Like this effective theory. But then it's semi-classical, okay? Then so in fact, even state is almost unique. For example, in Dosita case, if you just do the global slice, it's like antipodal. So it's not like a generic state.
Yes.
Okay? And it seems like a unique state because you're already going to the semi-classical state. And in that picture, to recover the same same entropy, then you do the tracing out. And in that picture, it looks like edge mode because it's tracing out. But that's the way real physics from boundary point of view to me is a microscopic states are there. There's a lot of different states and you coarse grain. So therefore, in the global picture, it looks like unique states. But if you trace out the other side, you reproduce same entanglement entropy, of course, because you just make it, enhance it and reduce it. So, and in that case, it looks like entanglement entropy, not like microstates coarse grain entropy. Therefore, you can map that to the edge mode.
Ah,
That's how I view.
I see. I see. Yeah, usually also its edge mode is associated with super selection sectors.
Yeah,
That's another idea. But your case is really entanglement.
Yeah, it's just really
different.
But then from the point of view of the observable, which is composed of this hard mode operator, it looks like almost.
Yeah. After tracing out, yes.
Yeah.
I see.
Yeah. So that's why semi-classical vacuum, infolding vacuum look unique. You can't access that thing.
I see. I see. Thank you very much.
Yeah.
Any other urgent question? Okay, so if not, let us thank Yasunori again. His great talk. Thank you very much.
Thank you.
So now it's a good time to go to second talk.
Yep, I probably unshare or something, right?
Yes, please.
Yeah. Share. Sorry. Oh, this one.
Yeah, thank you very much.
Okay.
Please.